Welcome to today's webinar titled Authentication Security of Combinatorial Watermarking for GNSS Signal Authentication, based on a paper published in the fall 2024 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Dr. Jason Anderson. Jason Anderson is a recent graduate of the Stanford GPS Lab under Todd Walter and Sherman Lowe. His research pertains to constructing efficient crypto systems for GNSS. Before Stanford, Jason received a mechanical and nuclear engineering degree from UC Berkeley and has worked at SpaceX and General Atomics. Jason will start work with Zona as a senior security engineer in a few weeks. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will turn the time over to Dr. Anderson.
All right, thank you. So let's get started. As Beth mentioned, this is based off of a paper to ION. And that paper covers two specific things. The first is the definition of what a combinatorial watermarking function is, and the security theory for a non-SER adversary. I'm going to define what an SER adversary is later, but this paper covers the non one. And then after that, in ITM in January, so this paper was submitted to ION about a year ago. After that, in January, we took this material and applied it to WAS. And I'll have a slide on that. And then for Pacific PNT in April, I did the theory for the SER adversary. So you all are welcome to check out the papers after this. So also this presentation and paper substantially contribute to my recent PhD defense. If you want to scan this QR code, you can go watch the presentation, and I should be ready to distribute my dissertation imminently. So if you're interested in a copy of that, just send me an email. Okay, so quickly for a quick introduction. So we've got data and ranging with GNSS, and usually those signals are XORed together, and the receivers track multiple satellites and decode the data, and then perform a trilateration problem. For the ranging component, the satellites are broadcasting a repeating beacon, something like a gold code, and the sequence is just going over and over again. The receiver is correlated shifted replica. That's what this diagram over here on the right is demonstrating, with the top being the shift, the bottom being the matching convolution, and when they're aligned, we have a high correlation, and then the highest determines the range. Now on to spoofing. So the problem with GNSS signals is that they're open signals, so anyone can download a GitHub repository and spoof the signal. This is our adversary, spoofing a plane. And then there are a couple of resistance strategies. We could sensor fuse, if the signal doesn't match the IMU, something's wrong. Directional antennas is a really nice one. If all the signals are coming from one direction on the ground, something's wrong. But the focus of this presentation is about cryptography. With cryptography, we entangle the GNSS system with mathematical puzzles that are computationally infeasible to solve without privileged information. There are two components. We can do data authentication. With data authentication, we can use standard crypto methods provided there's enough bandwidth. That's its own separate challenge. But today it's about ranging authentication. So current signals can provide authentication under certain assumptions, and watermarking is currently under consideration, but the security guarantees are not yet understood rigorously. So what's watermarking? So on the right, I have the same diagram from before, and now I'm going to switch it to a watermark signal. With a watermark signal, we'll take the signal and we'll perturb it. So here I've got these arrows here. So we took the original signal and we degraded it slightly. and this will induce a decrease in the matching convolution. So whereas the blue is the original, the red is the new. So we've introduced a degradation. Okay. Later, after this degraded signal is distributed, the receiver will receive a seed, a cryptographic seed on how to compute the perturbations. So there'll have to be two signal processing steps. The tracking step is we'll have a degraded signal. Then later, the receiver will go back and do a second processing, and they should experience an increase. And so this increase should provide authentication security. Now we got additional problems with this. So if when we take the signal and we add cryptography, now we've got this nice mathematical puzzle here, and that should deter these attacks where somebody just generates a false signal. But a more advanced adversary can have a receiving dish. So that's what's represented here. So even though the new advanced adversary, even though there's cryptography in the signal, this advanced adversary can observe the watermarks and repeat the signal. This is what an SCR attack, so security code estimation and replay adversaries, can observe and replay authentication features. And they might have individual beam steering repeaters, lots of technical equipment know-how. If the receiver has an onboard clock, there are some deterrents. So if the receiver onboard clock knows that has an uncertainty less than 5 seconds and it receives a spoof signal with the watermark 10 seconds later, then it should be able to reject those signals. So there's some, but eventually the adversary will get better and better, and this delay and loop will be very short. Okay, so now moving on to GNSS cryptography prior art. The big one is Galileo's OSNMA for navigation message authentication that should be starting up soon. They're considering some cryptographic ranging authentication systems with their ACAS proposal. But the main one is Chimera. Chimera is the AFRL's proposal for L1C that will have a watermark in the signal. And then I work a lot on SBAS because I work for Dr. Walter. So I usually apply the systems to SBAS since that's what our lab specializes in. Okay, so quickly here, so we have for the signal design, we have a data channel and a spreading code. My defense goes a little bit more into details on how to design the data channel stuff. So I'm going to skip these slides for the sake of time. So if you want to look at my dissertation, you'll talk more about this. But the important part here is from the data channel, I talk about how to derive a bunch of cryptographic materials. HP is just a random number, and I'll defer on why it's called HP to other things. But for the sake of this presentation, it's just a pseudo-random material. All it is cryptographic ciphertext. Okay. But the important part here is we're going to take this cryptographic pseudo-random text and we're going to generate a watermark. So we'll take this text and we'll create perturbations on the ranging code. That's all what this presentation is about. It's just how do we take cryptographic text and perturb the watermark to induce a watermark signal. So first, let's examine Chimera's watermark. So Chimera has navigation message authentication, and inside there they'll have signatures. Right now the proposal is ECDSA, but they might be switching to another protocol soon. But we'll take the ECDSA signature and compute a hash of that. That's what the circle represents. So now we've just got an integer. And from that integer, we're going to derive a location on the spreading code. So AES is just it's called the advanced encryption standard. I can use this as sort of like a random number function. And so what Chimera does is they take the L1C signal and divide it into sections. So each 1 millisecond section will have 31 sections of 33 chips. If I have that right. So I have 31 sections of 33 chips. So 31 times 33 is 1023. So among the 31, they'll use AES to select a random location. So they might select this section of spreading code, or they might select this section, or that section, or this section. It's just random from AES. Well, let's say they pick this section. So first they take the signature and use AES to derive a random section, 31, one of the 31, depending on whether or not there's other details there, but we'll just keep it simple here. They select a random section, and then they take that random section and replace it with an AES sequence. So they pick the random section, and then they replace the normal wheel code with an AES sequence. So now it's gone from a wheel code that's known to a random sequence. So the motivating questions of this work is, well, with a watermark, what's the distribution of the difference in correlation peaks? So I have this difference here, but if I subtract these two, so this is at 1,000, this is a 600 in our conceptual diagram here. So the difference would be 400. What's the distribution? Is it always going to be 400? It's going to be a normal distribution. What's the distribution of that? Because in order for me to know whether or not it's secure, I need to know its distribution. But before that question is answered, we got to understand, well, what's a good receiver statistic? So this correlation idea here is good for intuitive purposes, but it's not really the statistic a receiver is going to want to use. And then after we know that distribution, how much security does the watermark provide? So once we know the distribution, we can compute bounds and the tails. And then now we have to introduce an adversary. So if an adversary is in the mix, they're going to try and break it, or we're going to have to compute, well, if the adversary is involved, can they break my distribution and essentially fool my receiver? And then with the Chimera watermark specifically, there are additional modeling challenges. So replacing one sequence with another pseudorandom sequence yields a complicated interaction in the statistic space. So we're selecting a random section, and then we're replacing with another random section. It's kind of a difficult challenge to try and model that on the receiver statistic without doing experimentation. And then furthermore, the Chimera watermark is a burst. So we'll have normal wheel code, and then all of a sudden it'll just be completely random. So that means there's a time correlated aspect of it too, which can help with, which will degrade security. Okay, so again, we're back here. We're gonna talk about what's a good watermarking function for to perturb the spreading code. So what makes a good watermarking function? So step one, observation of one watermark chip should provide limited information about the other chips. So in the Chimera watermark, there's a burst. So if the security code estimation and replay attacker observes several chips that have been mangled, then it'll know that for the rest of that 33 chip section, the rest of the chips are mangled too. We want to make sure that observation of the watermark doesn't provide any information about other watermarks or other authentication features. And the main benefit of this work here is what I'm going to show is with the combinatorial watermark is we want the combinatorial watermark to have a tractable distribution. Tractable meaning I can compute that distribution, and then I can bound that distribution. Another nice thing would be that the watermark have a constant degradation. So if I'm replacing one random sequence with another random sequence, my statistic will be random. It would be nice if the watermark has a constant degradation and it's not random. So that's the subject of this work. What makes a good watermarking function, and how combinatorial watermarking functions are good watermarking functions. So the definition of a combinatorial watermarking is as follows. So let's say we have n chips in a spreading code. For instance, 1023 in the gold code. The provider is going to say r equals 15 and invert them uniformly. I'll talk about why r equals 15 later, but just for the sake of intuition, we have 1023 and we're going to uniformly select 15. So the watermarking function in my work, I specifically spell it out with two algorithms. And the point of those functions is to provide a one-way and uniform watermarking function. So we're going to take our 1023 bits and we're going to select among them uniformly, say 2 and 5, and then others. We have to make sure that it's uniform, so we don't want a biased watermark, and we want to make sure that it's one way. So what that means is if I observe 2 and 5, what information does it tell me about other secrets in the cryptography structure? So the paper goes into details on what one-way and uniform means and how the function satisfies those properties. In doing this, we ensure that entropy is spread across the entire spreading code, and every single cryptographic operation enacts a change. So when I take the wheel code from L1C and replace it with a pseudorandom sequence, sometimes the new sequence will align with the old sequence, which would mean no change. Okay, in this watermark, we're inverting. So that means every single inversion enacts a change. And because there's exactly 15, the degradation is constant. It's random, but the degradation will be exactly 15. Okay, so now it's time to evaluate the security of this watermark. So we have two adversarial models. First, we have to understand that one-way uniformity admits no efficient algorithm to guess a watermark. So that means that the only thing an adversary can do is to do an exhaustive guess. Okay, there's nothing in the function that says, well, I'm more likely to pick check number 2 than I am to pick check number 3. So the adversary could be a security code estimation replay capable. So the non-SCR adversary looks like this on the left. It's just they download the GitHub repository and create a false signal. The SCR adversary is listening to the signal, it's listening to the watermark and rebroadcasting it. So the paper goes over non-SCR. I'm going to go over SCR briefly based off of my Pacific PNT paper, but both of those resources go into more detail. Okay, so for the non-SDR adversary. So the adversary may only use exhaustive guessing when attempting to spoof a receiver. So that means they just got to guess a watermark and roll with it. What's nice about combinatorial watermarks is they lend to vast search spaces. So in our example, 1023 choose 15, there's 2 to the 109 possible combinations for each millisecond watermark, which this number is enormous. So the goal here is to create a search space that's so vast it's infeasible for someone to look for it. They just have to pick one and go for it. But the adversary can elect any number of chips in the signal to spoof. So this is really a decision problem for the adversary. So let's say for the moment that the provider is picking 15 pseudo-randomly. The adversary could pick 15 and roll with it. The adversary could pick 500. I have to account for any adversarial strategy. They could pick 1, they could pick 5, they could pick all of them. So, and then the receiver is going to have to use statistical processing. So that statistic is defined as follows. So here on the bottom, I have my typical tracking loop. R stands for replica. And then I's and Q's. So this is my correlator box. So the first thing the receiver is going to have to do is they're going to have to take their samples and put them into memory because the watermark is unknown at distribution. Later, it'll be revealed, but for the moment, it's unknown. So they'll have to store the baseband samples, and then later the watermark will be revealed. And once it's revealed, the statistic that the paper suggests is called, I call it R delta in this slide, and you'll see why, but it's just a subtraction. So R stands for replica. This could be the wheel code. It could be the CA code. But the RW is watermarked. Okay, so we'll have the subtraction. So that's what this gain is, or this linear filter is. So for intuition's sake, I want to note here that RW, so the watermark replica minus the replica, is mostly zeros. Okay, because they're mostly the same. So the subtraction would be mostly zeros. But in our intuitive example where there's 15 flip chips, there'll be exactly 15 ones or minus ones inside that. Okay. So now let's compute the statistic distribution. So for an n-bit spreading code where R chips are flipped by the provider and an adversary who uniformly inverts S chips. So the adversary gets to pick. You get to pick S of them and transmits to the L-type filter R delta. The resultant distribution is called the hypergeometric distribution. So neglecting noise for a moment. So what's nice about this combinatorial watermarking is I can derive the distribution of the statistic, right? This is cool because now I can take this distribution and compute bounds. With noise, we can incorporate the additive Gaussian noise. So we have we can add the noise to the distribution, and we can add the noise with convolution, which means I can still compute the distribution. And when I look at multiple watermarks, I can use repeated convolution to compute. Let's say I'm looking at, say, a whole second worth of watermark, and my 1 second is composed of 1,000 individual watermarks. I can use convolution to compute the distribution even in that case. So I can compute that's the important part here. I can literally compute the distribution induced by this watermark in the presence of an adversary. So you don't have to take my word for it. So I've experimented with real data to show that this distribution is correct. Okay, so this is with WAS, and WAS right now doesn't have a watermark. Okay, there's no watermark in WAS. Okay, so how do I experimentally validate? Well, in a real system, in a real authentication system, I have a watermark signal, and the receiver will track using the regular gold code replica. Okay, I can test on a mirrored problem. So in my software-defined radio, my receiver tracks the unwatermarked signal with a watermark replica. So I essentially switched R and RW. So this experiment is with data from, I think, June. This shows the authentic distribution of Y delta and the spoof distribution of Y delta, looking at 60 watermark increments. So I'm aggregating over 60 milliseconds for each of these. A real receiver might look at a second. When I want to look at the second, the distributions are so narrow it doesn't look like a pretty picture. But anyway, so in this case, on the left, I have the spoofed case. I have an adversary, and I'm simulating an adversary selecting random watermarks, and this is what the statistic of Y would look like. It's pushed over here. And with the authentic case, distribution is over here, and clearly they're separable. So now I can start putting false alarm and misdetection bounds. So yeah, so these solid lines are directly computed via convolution. So there's no central limit theorem assumptions. So the paper on WASP from ITM, essentially, now that I verify that this distribution is accurate, now I can implement the next step, which is design. So I've got a couple diagrams from that paper here. Now I can start answering new questions like, what is the minimum chips that I want to introduce in my watermark for a specific security level? So in this diagram on the left, I have 32-bit security. So that means there should be a 1 and 2 to the 32 chance. That's 10 to the minus 9 chance of spoofing. This is a comparison of my integration time versus the number of chips that need to be inverted. So if my receiver is looking at 100 seconds, it needs less chips versus 1 second. So there's an inverse relationship. And on the right-hand side, this is a similar diagram except with C over and not. So if I have a specific confidence level on my noise in the system, then I can specify how many chips are inverted before I have certainty. So notice these are inverse relationships. So the higher the noise, the longer the integration time needed. The higher the chips inverted, the lower the integration time needed. This is a design element. This is not experimental. This is using the distributions that I've derived. So now moving back to our last couple slides remember there were 2 adversarial models. So this paper covers this one. Now let's talk about the SCR adversary. So in order to deal with the SCR adversary, we have to introduce a second statistic. So this is called R sum. So the nice symmetry here. So this is the watermark replica plus the normal replica. And this is mostly ones, except for exactly 15 zeros in our intuitive example. So essentially, we have a dual statistic paradigm. Okay, our delta measures how well the adversary can predict where the watermark chips are, and our sum is how well the adversary will track the spoof signal. And this is why we have this dual statistic paradigm. So we have an adversary that's observing the watermark. Here's our adversary, and they're repeating it into this receiver with two statistics. The adversary has a decision problem. When they observe a watermark, they're going to have to decide, is this particular chip not flipped or flipped? Okay, so this is just an intuitive a BPSK constellation probability distribution at SNR 3.0, just to demonstrate stuff. The adversary is going to have to pick a decision boundary. So it does its best with its dish and radio equipment to make a measurement on whether or not it's normal chip or watermark chip, and they have to make a decision boundary. But the adversary can pick any decision boundary they want. A sensible one might be halfway in between, or they can use the Bayesian probability theory to say, well, it's more likely that it's not flipped than flipped. So maybe my decision boundary should be over here. But it doesn't matter. Adversary gets to pick that decision boundary. We have to account for every single adversary. So when the adversary uses a hard decision decoding strategy, the distributions are binomial distributions. So depending on its radio equipment, the main parameter of a binomial distribution is the error rate. So if I have better radio equipment, I have less error rate, right? And then I'll have more confidence on whether or not a chip is watermarked or not. But so the same idea with the hypergeometric distribution for the non-SER, but this is now a binomial distribution. So we have a decision boundary, and on the left here is my adversary. They get to elect a boundary. And on my right, I have the Y delta statistic and the Y sum statistic from before. The authentic distribution is going to be here. And my spoof statistic is going to be here, but depending on the adversary selection, it will traverse this trajectory. So I'm going to see if I can play here. So depending on what the adversary elects on their decision boundary for the chip estimator, the spoofing distribution is going to traverse this trajectory. Okay. So this trajectory I derived in the Pacific PNT paper, and it's a level set function on SNR. So the better the SNR for the adversary and their chip estimation problem, the closer these two distributions are going to get at the point where spoofing is going to be feasible. So so now I'm going to final slide here. I'm going to describe, well, how is combinatorial helped? So this is a lot of information. So first, combinatorial watermarking enables tractable distributions and receiver authentication statistics. I don't need to experiment. I don't need to use the central limit theorem. I don't need Monte Carlo simulation. I can compute the distributions. For the non-SER model, it's the hypergeometric distribution, and for the SER model, it's the binomial distribution. Once I have the distributions, I can compute the false alarm and misdetection probabilities without a CLT or other assumptions beyond the AWGN assumption. So that's the slide about those inverse lines. I can now, this is now a design problem. And then I can answer new questions like what design will minimize the degradation for a specific security level. So it means I can, the chimera is proposing a specific degradation, and it's parameterized. Let's say, well, we might want to watermark 5%, 10%, or 15% of the signal. Well, now we can answer, well, what duty cycle of watermarking will provide what security level? So I'm going to end on this slide. So again, feel free to watch my dissertation defense, scan the QR code, and you can also email me and request a copy of my dissertation when I have it, which hopefully will be in before the end of this month. So that is it for my presentation today. Thank you for watching, and now I'm happy to accept questions.
Thank you, Jason, for this great presentation. Like Jason just said, we'll now accept questions from the audience. As a reminder, you can submit your questions using the Q&A button in the viewer. And to just go ahead and get things started, Jason, we do have a question for you. In your presentation, you suggest inverting 15 chips per spreading code. How much signal degradation is that?
Right. So the 15 chips actually comes from the ITM paper where I say what chips are needed for 32-bit security. So at 15, so WAS has a 6-second time to authentication time. So there's a 6-second parameter in that detail. But if you go to this curve, 15 chips in 6 seconds gives you a 32-bit security. With 15 chips, the degradation is going to be twice that because I'm taking every positive one and subtracting it and turning it into a minus one. So that's going to be 30 out of 1023 degradation, which is about, let me compute that real quick. 30 divided by 1023. That is a 3% degradation. So that means that you can afford 32-bit security with a 3% degradation on the WAS signal with a 6-second integration time. So thank you for the question.
Thank you. Looks like we have a question from the audience, and this is, how will you handle signal and CN0 degradation in challenging environments when the maximum sensitivity is required? Not sure if I...
Yeah. So that is another good question. So the 15-bit assumes a C over a naught of 30. So that means you have full discriminated power with a 30 C over a naught. In the ITM paper in January, I examined two schemes. So with 30 C over a naught, you can flip 15. With a 25 C over a naught, you can flip 50. So essentially, the model assumes a worst case noise scenario, and I picked 25 and 30 because I thought that aviation receivers would not track a 1 millisecond integration time signal at those numbers. But so essentially, you right now you pick a noise model, and then I can compute the answer. And the noise model I picked for that one was 30 or 25 CN naught. So the noise is handled in these distributions. So you just, unfortunately, you just got to pick the noise model and live with it. But let me clarify, even at that 30 CN naught level, there should be a 10 to the minus 9 false alarm and 10 to the minus 9 misdetection requirement. So hopefully that's good enough. I think that's like 1 every 150 years or something.
Thank you. We have a follow-up to that question. Any idea how to combine NMA with watermarking?
Yeah, so that is the entire main theme of my dissertation. I didn't go into that, but so a key factoid here is that watermarking requires no additional bandwidth if you use Tesla as your authentication scheme. So that's what this diagram is about. So I can use cryptographic operations to derive as much pseudorandom material as I want. So the answer to your question is in my dissertation, but as a preview, you should be able to add a watermark to any signal without additional bandwidth, provided there's NMA in there. If you have NMA in there, you don't need additional bandwidth.
Okay, thank you. We'll just give it a few more moments here to see if anybody has any last minute questions. We'll just hang out for just a few moments just to see if anyone has any last questions. Okay, one last question here, and this is also going to be a follow-up. Does this mean that the watermark is derived from the over-the-air NMA key?
Yes. So with the SBAS proposal in the January ITM paper, currently, let me go to my prior work slide. So before I did all of this watermarking stuff, I assisted with the design of SBAS navigation message authentication. I got my little, there's my little icon here. Yeah, so SBAS navigation message authentication. And in that Tesla proposal, they're sending a key every 6 seconds. So that's where the 6-second watermark integration time came from. So essentially, in that proposal from the January ITM paper, there's a watermark, there's an individual watermark every millisecond, but the receiver will aggregate 6 seconds, so 6,000 watermarks together every 6 seconds, because the watermark derives directly from the NMA key. So the main selling point here is, so ICAO is standardizing the SBAS, Navigation Message Authentication Protocol, with WAS and etc. That means that we could add a watermark to SBAS without changing the ICD, which is really cool. So all you would need to do is, and this is what my dissertation talks about, so we can use what the designs Tesla means stands for time deficient stream tolerant authentication. So it's different than ECDSA and other cryptographic protocols, but essentially you can take one key and derive lots of other keys. That's what this is about. HV stands for hash point, and I in my dissertation I talk a lot about geometry, the geometry of the cryptography. So that's why it's called a point in my dissertation. But we'll take the distribution, the NMA distribution, derive as much material as we want, and then have from that material derive the watermark. So this key derives other keys. These keys do the navigation message authentication HMAC. So these keys are for the ephemerides, and these keys are for the watermark. But all of these keys are derived out of band. So we'll take the over-the-air key and derive navigation message keys, and we'll derive watermark keys without burdening the bandwidth.
Great. Well, thank you everyone for joining us today, and thank you, Jason, for your time and preparation. We want to remind everyone that a recording of this webinar will be posted to our website, YouTube channel, and social media by this Friday, the 6th. So thank you again, and we look forward to having you all join us for a future ION webinar.
Thank you, everyone.